Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosine River College in Sacramento, California. This is a continuation of a video series on hyperbolic functions. You should have watched, hopefully, a recreational interlude, Euler's formula, and I forget what else that title was, to be honest with you, and the unit circle, and then an introduction to the hyperbolic functions. In this video, we're just going to talk about the hyperbolic identities, which are very similar in form to the trigonometric identities. We know, for example, in trig, that sine is an odd function. Well, the hyperbolic sine is also an odd function. Sinh of negative t is negative sinh of t. We know in trigonometry that cosine is an even function, and the hyperbolic cosine is as well. The cosh of negative t is cosh of t, so it's an even function. Here's where we start to step away from the same exact results. So we know cosine squared for the trigonometric functions, cosine squared of t plus sine squared of t is equal to 1, because the hyperbolic identities are based on the hyperbola, which is x squared minus y squared. The cosh squared of t minus sinh squared of t is equal to 1. So it is not an addition, it's a difference identity. And then we have the relevant other Pythagorean identities, although these are not Pythagorean, but the other identities here. For example, this one right here, you would get by dividing all three terms of this identity here by the cosh squared. If you did that, you'd get 1 minus sinh squared over cosh squared, which is tanh squared, is equal to 1 over cosh squared, which is sech squared. So that's how you would derive that fourth identity there. And then we have these other ones, the sum and difference of angles identity. Now, just to let you know, the sum and difference of angles identity for the for the sinh is the same as the sum and difference identity for the sine. Remember, sine of A plus B is the same thing as sine of A, cosine of B plus sine of B, cosine of A. That same identity holds here for the hyperbolic sine. However, the hyperbolic cosine is not completely, but different than the regular old cosine identity. The regular old cosine identity was that you had the cosine of A plus or minus B. That turned into the cosine of A, cosine of B. But then if it was a plus, it would become a minus. If it was a minus, it'd become a plus, and you would have sine of A, sine of B. And with the hyperbolic functions, it actually keeps the sign. So if it's a plus, it's a plus. If it's a minus, it's a minus. So that is the difference there. All right. So we're just going to pick one of these to prove. It actually doesn't really matter which one of them. They all are proven basically the same way. And we've already proved this guy right here. And I verbally proved that one. So let's go ahead and let's prove one of the cosine one, the hyperbolic cosine ones. So let's prove maybe the cosh of A minus B. Let's do that one. So proof of cosh. I'm so used to writing cosine. You're going to do this too, by the way, when you go to work with the hyperbolic cosines and hyperbolic sines, is you'll want to write it as cos and sine. But just remember there's an H there. You want to prove that the cosh of A minus B is equal to cosh of A, cosh of B minus sinh of A, sinh of B. Well, let's see how this works. The first thing I'm going to do is trade the cosh out for its exponential form. So this is e to the A minus B plus e to the negative of A minus B all over 2. Turns out the hyperbolic identities are easier to prove because they're just manipulations of exponential functions. Okay. And if you can't see where to go from there, which I kind of don't blame you, that would be a little bit difficult to see where to go, then I'm going to stop there and take a look at the cosh. Whoops, again, there I go doing that. I'm going to look at the cosh of A times the cosh of B minus the sinh of A times the sinh of B. And again, I'll look at those, that expression in exponential form. So that'd be e to the A plus e to the negative A over 2 times e to the B plus e to the negative B, again, over 2. And then minus the sinh, which is, e, again, sinh of A, e to the A minus e to the negative A over 2, and times e to the B minus e to the negative B all over 2. Now, we're claiming that this picture is the same as this picture right here. Even though they don't look like they're the same, we're claiming that they are the same. Now, I'm going to go ahead and glue these two together because these two fractions here together, because it is one term out front. I'll just highlight it to show it. This is one term, and then this is a second term. I'm going to glue those together because they have the same denominator already. So let's just go ahead and do that. This is going to be equal to e to the A plus e to the negative A times e to the B plus e to the negative B minus e to the A. Well, you get the point. I didn't need to actually step through all that. You know the mathematics there. Now we're just going to multiply things out. So again, I'm just going to pause while I multiply out those binomials, just because it's a lot of mathematics in there. And it's no point. You guys have already passed a lot of math, so I can kind of skip some of the stuff here. That's what we get when we multiply everything out. And you would be able to see some differences here. For example, we have an e to the A plus B here, which cancels with the e to the A plus B there. We have a negative e to the negative A minus B, and we have a positive e to the negative A minus B. So those two cancel. In the end, things compress down significantly. We have two of those e to the A minus B's. Let me just showcase them here. It's this guy, A minus B, and this guy, A minus B. And we also have two of those e to the B minus A's. But I'm going to write those e to the B minus A's as e to the negative A minus B. And that comes from, again, this and this. I'm just grouping them up, and then obviously B minus A is the same thing as the opposite of A minus B. And finally, that's all over 4. Obviously, all of these are divisible by 2, so it's e to the A minus B plus e to the negative A minus B all over 2. And let's see where we wanted to end up. Oh, that's what we wanted to prove. So notice those two highlighted things are exactly the same. That is the cosh of A minus B. So that's how a lot of these proofs go. They're very mechanical. It's what a lot of students hope they get on an exam, is a proof for a hyperbolic identity, just because they're kind of easy to do. So let's go ahead and do another one. This is one of my favorites, actually, just because of the sheer implication here. So I'm going to write it as a single line so that you guys could see it. This is saying that if you have the cosh of a number times t plus, oops, that's not true. This is saying that you have the cosh of t plus the sinh of t to whatever power you want. This will equal, it's, by the way, a natural number power, but this should equal the cosh of nt plus the sinh of nt. Now, this tends to lead people astray a little bit, but such an interesting result that if you take a power, a high power, 100th power, for example, of cosh plus sinh, it's just the cosh of 100t plus the sinh of 100t. That is, to me, an amazing statement. Normally, when you're doing a proof that's true for all natural numbers, which is what we're doing here, you would use, or you'd be inclined to use a proof by mathematical induction, but you don't actually have to do that here. You can just do a regular proof using the exponential form. So I'm going to go ahead and start on the left-hand side here. I'm just going to say proof. I have the cosh of t, and I'm adding to that the sinh of t, and we're raising that to the nth power. Well, the cosh is e to the t plus e to the negative t over 2. And the sinh is e to the t minus e to the negative t over 2. We're raising that to the nth power. If you add those two up, you'll get 2e to the t plus e to the negative t minus e to the negative t, so those two cancel, and it's over 2. And obviously that's e to the t raised to the nth power, which is e to the nt. Now, interesting thing about this is that I think what's more powerful than what the result of this theorem is going to be is that cosh of t plus sinh of t is actually just e to the t. And then if you raise that to the nth power, that's e to the nt. I just think it's kind of neat. Now, we want to arrive at, this is the cosh of nt plus the sinh of nt. Well, that you can do off to the side here. Cosh of nt plus sinh of nt. Well, that's equal to e to the nt plus e to the negative nt over 2. That's cosh. Plus sinh e to the nt minus e to the negative nt. Again, over 2. They're all over 2. Add their numerators. You have 2e to the nt. And then e to the negative nt minus e to the negative nt, they cancel. And so this just becomes e to the nt, which we have just proven is equal to the cosh of t, I almost said the cos, the cosh of t plus the sinh of t raised to the nth power. QED, we've done it. Very interesting statement. That's a really neat result. So hyperbolic trig functions are very, very nice and simple to prove. Usually it's like that way. I just highly recommend start with the exponential form if you can.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.